page, I think, of the paper, and now the title page.
Okay, so I'm not really sure that if this is really an isogeometric algebra, but it seems to satisfy the criteria, but it is closely related to the idea of an isogeometric algebra. So let me just start then. We'll only be talking about two geometric algebras, and that's G3, which is generated by the Pauli matrices E1, sigma 1, sigma 2, sigma 3, or I call them E1, E2, and E3. And the closely related geometric algebra G11, that's the Clifford algebra generated by two elements, which have one has square plus 1 and the other has square minus 1. So here we have.
Just a quick question. Is G11 equivalent to complex numbers?
Not really. It's equivalent to real 2x2 matrices, whereas G3 is equivalent to real complex 2x2 matrices generated by the Pauli matrices.
But this notation 1, 1 is referring to the signature of the metric.
That's right, the signature of the quadratic form. So it has.
This quadratic form would be the one associated with complex numbers, wouldn't it?
Actually, G3 is more closely associated with the complex numbers because it's the complex 2x2 Pauli matrices, 2x2 Pauli matrices, whereas G11 is isomorphic to real 2x2 matrices, as we'll see here. Okay, so for G3, it's as a real geometric algebra, it's spanned by 3 unit vectors, E1, E2, and E3, which have square 1. And then it has 3 bivectors formed by taking pairs of them, E1 times E2, E1 times E3, E2 times E3. And then you see, now you get the complex number I is a trivector, or the pseudoscalar element of the geometric algebra G3. That's E1 times E2 times E3. So I, which is the square root of -1, has the interpretation of a 3 vector in the geometric algebra G3. So here we have it. The quantities E1, 2 is just the product of E1 and E2, anti-commutative for E1, E3, and E2, 3. Unit bivectors, you can think about that as being along the XY, XZ, and YZ plane, which in bivectors have, Euclidean bivectors have square -1, as we see in this line right here. E1, 2 squared is E1 times E2 times E1 times E2, but now associative law is always true in geometric algebra or Clifford algebra. So E2 times E1 is equal to minus E1 times E2. So if I flip that, then I get minus E1 squared, E2 squared is equal to -1. Okay, so again, we see that the complex number I, which is formally just the square root of -1, now has a geometric interpretation of a unit trivector, namely E1 times E2 times E3, but also has square -1. Okay, now this is very important equation number 1, and that's writing the basis. So what I call the spectral basis consists of U plus, which is this element here, 1/2, 1 plus E3. So if you square that element, you get, it's an idempotent, you get the same thing back again. So the interesting thing is to note that we can write that as a product of a column matrix, BA times an A, BA times B. I'll explain this multiplication in a minute, but what you have is BA squared, which is the same thing as U plus. E1 times U minus is B. And then we have A, which is the same thing as E1 times U plus, and then we have U minus as A times B. So again, this A and the B are nilpotents. Okay, let me get to the next page. You can see this is the multiplication table of the nilpotents A and B. Okay, so it's just so a nilpotent is any algebraic quantity which has the square equal to 0. So A squared equals 0 is equal to B squared. But then we have the product AB and BA. So you have A squared is 0, A times B is AB, A times AB is 0 because A squared is 0 times B. And you have ABA. Well, you get A back again then. And then for B times A is BA, B squared is 0, BAB is B, B squared A is 0 because B squared is 0, and so on. So it's a very easy multiplication table. And let's see. Okay, I'll show you in a minute. Okay, so here you have I call them A and B are said to be compatible nilpotents because they satisfy the rules. Well, they're nilpotents because A squared equals 0 is equal to B squared. And we say they're compatible nilpotents because if you sum them, AB plus BA, you get 1. Well, in a certain sense, that's like a duality statement. It's a way of writing a duality, but it's quite a little bit different than the usual form of duality because we're considering A and B as elements of the geometric algebra. Okay. So again, the multiplication table is very easy to remember, which I gave here. Now, if we define F equal to A minus B, and I, again, is still equal to E1 times E2 times E3, that's the unit trivector of G3. So here you have it. G11 is equal to E1 and F. Well, usually I write, well, here you have E1 is equal to A plus B, so we could call that F1 because that's A minus B. But you see, F is interpreted as a vector of G11, and F has square minus 1. Let's see, where do I? It's very easy to prove these things, but I can't put everything down. So again, think about I as interpreted in G3 as the square root of minus 1. Okay, so we can easily create the corresponding element A in the geometric algebra G3 by writing it like this: BAA times this 2 by 2 real matrix. Okay, A11, A12, A21. If you consider A11 and A to just be a real matrix, then you get the geometric algebra G11. Okay, but if you can let these be complex numbers, namely where I is again equal to E1 times E2 times E3, then you get the geometric algebra G3. So you can see really the only difference between the algebras G3 and G11 is the interpretation of the various elements. So well, let's see where I have this. Okay, well, here you see the matrix equivalent then. So here you see the Pauli matrices. E1, that's like sigma 1 for the Pauli matrix, is just the diagonal matrix, 1, 1. E2, well, you just multiply this by I. Well, no, you have to change this to minus I and I here to get E2. And E3 is the usual Pauli matrix, 1 minus 1. Okay, so again, this is interpreting the matrix of E2 is a complex matrix because it's in the geometric algebra G3 here. Whereas, notice what F is. F is just 1 and minus 1, you see? Well, if you multiply I times F, you get E2. But, so you see, in the geometric algebra G11, F corresponds to the matrix minus 1, 1. Well, that matrix, if you square that, you'll get minus the identity element. So that corresponds to F in the geometric algebra G11, which has square minus 1, because this matrix has square minus 1. Notice the idempotence A, the matrix of the idempotent A is simply 0, 0, 1, 0. Well, obviously, if you square that matrix, you get 0. It's an idempotent, a nilpotent rather. The same thing for B. B is 0, 1, 0, 0. If you square B, you get 0. Well, that's a nilpotent. The corresponding nilpotent matrix corresponding to the geometric nilpotent B in the geometric algebra G11. See, A now, if we consider A to be a complex matrix, that's where we're interpreting I as equal to the unit trivector, then A11, A12, A21, A22 are complex numbers then formally, because E3 is in the center. It commutes with all elements in the geometric algebra G3. It also commutes. So again, if you consider A11, A12, A21, A2 to be real numbers, then we're talking about the algebra G11. So it's just a different interpretation of what a matrix means. Well, this is a coordinate matrix. This is the coordinate matrix in the geometric algebra G3. And if you consider E and F, well, E1 and F1, E1 is just 1, 1. Well, that's a matrix which has square plus 1, the identity matrix plus 1, whereas F, this matrix 1 minus 1 has square minus the identity matrix then. So you see that's why I call these matrices matrix. These are the usual Pauli matrices here. So these are the generators of the geometric algebra G3, whereas A and B are generators of the geometric algebra G11. But in that case, A represents a real matrix. These A11, A12 are real numbers then. But in the complex case, when we interpret them as complex numbers, then it becomes a Pauli algebra generated by the Pauli matrices, which are usually represented by sigma 1, sigma 2, and sigma 3. Okay, I do give...
Dr. Sobczyk, did you just say that A and B were the generators of G11?
That's right. That's right. That's the...
but isn't right. Isn't F a generator of G11?
Well, no, you don't. F is equal to A minus B. So it's so any real linear combination of A and B of these matrices here, you'll get.
But a few paragraphs above, like if you just, could you go a little bit higher, a little bit more? Yes, there you wrote G11 is the just the paragraph under equation 2. The G11 is generated by E1 and F.
Yeah, F is equal to A minus B. So you see that's this matrix here. You see that number 4.
Yes.
Look at number 4. That's F.
But my only point was that you had already written that G11, the generators of G11 are E1 and F. Is that
well, you consider, generally we just consider E and F over the real numbers. Now you multiply them, you also have the bivector E times F.
Yeah, I think it's it's all correct. You need 2 elements for the generator G11. One has to be idempotent.
Yeah, that's right. So I don't really need F here, but I just put it in there. So any 2 of these would generate the algebra, really. over the real numbers, you see. But if you square A and you square B, you get 0. But F squared is equal to -1. So that's minus the identity element.
But as a generator, F acts like the complex unit. Right?
Well,
Is that-
if you square the matrix 1 minus 1, you get minus the identity matrix. You don't.
From 61320
I'm sorry. But
Yeah,
F squared is -1.
Yeah, that's right. Yeah, so again, the geometric algebra G11 is generated by any two of these elements. That means you include multiplication. So A times B, actually, if you multiply A times B, you get the matrix 0, 0, 0, 1 with a 1 down here. BA is a matrix. Let's see, do I give that or not? Oh, yeah, I don't have it down here. But that's the thing. You see, BA, BA corresponds to a 1 here. AB corresponds to 0, 0, 0, 1. So that's right. So you should understand this, what I call the spectral basis. This is the element in geometric algebra, which corresponds to 1, 0, 0, 0. So again, BA is just the matrix of the element BA is 1, 0, 0, 0. Is that clear? So, well, you can see, let's see, where is it? Where do I have that? Okay, here you have it. So you have A11 times U plus. Well, okay. U plus is right here, you see. So U plus corresponds to BA. That's the matrix of U plus is 1, 0, 0, 0. That's why we keep to just 2 by 2 matrices is the simplest case here. So you can see the exact correspondence between a matrix and the geometric number which it represents, either in the geometric algebra G3, which if you consider the matrix A11, A12, A21, A22 to be real numbers, then that corresponds to G11. But if you consider these to be formally complex numbers, then we have the geometric algebra G3. So again, you have U plus, that's just the matrix with 1 in the place of A11, 0, 0, 0. Okay, E1 times U minus is B. Well, that corresponds to 1 in this place and 0. Okay, you can see E11 times U minus is B. Okay, anyway, the matrix, well, these are the Pauli matrices. So you can see these nilpotents, excuse me, and somehow these nilpotents are the matrices correspond to just a 1 in either lower, or that's A corresponding to 1 here, B here, of course, E1 then is A plus B, okay, or Z, I call it A plus B, and F is A minus B, 1 minus 1. The notation is a little confusing because here we use E3. Well, I don't want to call that, I really should call that EF1 to correspond to E1 is A plus B, and F is A minus B. Remember, A corresponds to a 1 here, B corresponds to a, well, A minus B is F then. Okay. But again, I emphasize how easy this multiplication table is. It's very easy to remember because A squared is 0, ABA just gives you A. So that's interesting. A times BA, well, you've got B in the middle of ABA, and that corresponds to A. Whereas if you take BAB, then you get B. So it's very easy to remember that multiplication table. Also note here, so whereas F is a vector in the geometric algebra G11 is represented in the algebra G3 by the bivector E1 times E3, which is, okay, so you see so you can see that G11 is contained in the geometric algebra G3, but it's represented by the bivector E1 times E3, which is, well, that's a little bit strange. And that's why they say a matrix really, most people think about a matrix as just a table of numbers because, well, when you start giving a geometric interpretation, then you get this ambiguity between a bivector in one geometric algebra is a vector in another geometric algebra, namely F is a vector in the geometric algebra G11, but if you write it as a sub-element of the algebra G3, then you must choose it to be the bivector E1 times E3, which is the bivector representing the XZ plane. So, but again, that's like a quaternion then. So you can say that F is a quaternion.
Excuse me, one elementary question, maybe. But we can say that for the G11, we need two elements for generating that algebra. That's right. And for generating the G3 algebra, how many elements we need?
Actually, if you consider it, you really only need what, E1 and E2, because E1 times E2 is equal to I times E3. So if you consider, you can consider the polyalgebra is generated by E1 and E2, is it not? E1 and E2 over the complex numbers, because, well, where you're identifying E3 is equal to I times E1 times E2. Okay.
Okay.
So in that sense, you can say that G3 is generated by E1 and E2 over the complex numbers then. I think that's correct, right?
Okay, thanks.
Yeah, that's right. Well, that's right. You interpret E3 as I times E1 times E2. So that's a little bit strange though, but as a real geometric algebra, then G3 is generated by E1 times E2 times E3 over the real numbers then. Any element in the polyalgebra.
Because G11 is contained in G3.
That's right. Whereas you interpret F as a unit bivector.
Yes.
Which is a little bit strange. That's why people, I guess, don't do it. Okay, well, here's a representation. E1 is E1 times U plus times U minus. Okay, that's just 1, 1, you see. So again, these are just the basis elements that represent E3 is U plus minus U minus. So that's just another identity. Okay, I do include at the end of the paper, I include references. And you can see Dr. Santilli's paper and also this Rocha and Jaime Vaz Jr., which is an important reference on, as Dr. Santilli pointed out, on isogeometric algebra, the standard way of looking at isogeometric algebra. So we'll go back here though. I will send copies of this new version. Okay, so there we have that. So I think you're clear now. G3 is a geometric. The coordinate matrices of G3 are the standard Hermitian polymatrices, whereas the coordinate matrices of G11 are the real 2x2 matrices then. So these geometric algebras, G11 and G3, are very closely related. Namely, one is generated by complex 2x2 matrices and the other is generated by real 2x2 matrices.
Provided that one is idempotent.
Yes, that's right. Okay, well, I think I've gone over this material already, but this is the standard ISO poly algebra that we talked about earlier, where Dr. Santilli introduces the matrix of the ISO poly matrices as e to the phi, e to the minus phi, sigma 2 hat is this matrix, and sigma 3 hat is this matrix. So of course, the difference is with E3 as a standard matrix, we have 1 and minus 1. But with the ISO matrix correspondence, you have, well, that'd be cosh phi plus sinh phi, and this would be minus cosh phi plus sinh phi. Well, that's interesting because as we saw in the paper that Dr. Santilli, in my paper, which was now happily accepted, it makes this distinction in the paper as well, the geometric interpretation as a geometric algebra. Okay, so I'm just writing this now in terms of these, the bases U plus and U minus as we had before. And you see how it looks stated as an element of the geometric algebra. Okay, but then we have what's called an ISO unit, a very important idea, which arises in isogeometric algebras. In this case, the ISO unit is cosh phi plus E3 sinh phi. So it's a mixture of a scalar and a bivector, but it can be nicely written as E to the phi E3. Whereas the T matrix, which we call T hat, is 1 over this matrix here, and it becomes E to the minus phi E3. So I find confusing, and I sometimes make the mistake of which multiplication you're referring to, either the geometric algebra multiplication or the isogeometric algebra multiplication. That can be sometimes very confusing and cause problems.
Until here, we are only speaking about one subset of the G3 algebra.
That's right. It's just another way of looking at the elements. It's a reinterpretation of the elements of the geometric algebra G3.
Okay. Mm-hmm.
And hopefully this geometric interpretation is significant. That's what Dr. Santilli and I wanted to pursue in a future paper, is to how this geometric interpretation impacts on Dr. Santilli's theory.
Mm-hmm.
But again, it's all the elements are interpreted in the geometric algebra G3, which we now call isogeometric algebra, but the elements are really just a shuffling of what we mean by a bivector and a trivector and so on. They have different geometric meanings. The significance of that, as far as physics is concerned, well, that I cannot say I have the answer to that. I hope that this research will help provide the key to that interpretation that we'd like to find. Okay, well, just looking at the E1 squared is equal to 1. Well, also in the isogeometric algebra, sigma 1 hat, the corresponding square is equal to 1 and so on. And we have the same basic ideas, but note that the trivector in the isogeometric algebra is a mixture of a trivector part times cosh phi plus a bivector sinh phi. So again, it's a reshuffling of the elements in the geometric algebra G3. Well, this is interesting because we can consider the isogeometric algebra element sigma 1 hat to be a Euclidean, well, a Lorentz boost of the element G1 or E1 in the standard geometric algebra. The same thing with sigma 2 hat as a Lorentz boost of E2. So it looks to me like the geometric significance of Dr. Santilli's isogeometric algebra are represented by boost velocity transformation in the usual geometric algebra G3. Okay, so again, A hat, the corresponding element in the isogeometric algebra is just A times the iso unit element, which is e to the phi E3 and so on. That's equivalent to saying that, oh, okay, here's you can see that A hat, okay. Yeah, this shows you that one hat is the iso unit in the isogeometric algebra, okay? But it corresponds to the element in the geometric algebra G3, A times e to the sigma E3. Okay, well, I'm trying to do a little bit of this isogeometric multiplication. Well, this is the definition of it. A star B is A times T hat times B. And that's just the same thing as A e to the minus phi E3 times B. Well, again, here's the basic formula. A hat times B hat in the isogeometric algebra is AB in the standard geometric algebra times the iso unit e to the phi E3. Okay, I try to write down a corresponding basis in the isogeometric algebra in terms of the standard basis in the G3 then. Okay, so now I'd like to talk about what I call isogeometric algebras, but a new way of looking at it. In this case, what we do, we take compatible null vectors A1 and A2, a pair of compatible null vectors, A1 and A2, and B1 and B2, which satisfies the same type of constraints that we saw on the first page. Okay, maybe I'll go back to that quickly so you can see it's no different. If I go back here. Okay, this was a defining relationship between compatible nilpotents. Okay, A and B have square 0, and they have this duality type property. It's like a dual property. AB plus BA is equal to 1. Okay, so now what I'm doing down the next, I'm taking two pairs of compatible nilpotents. Okay, so that's one pair, A and B, which I'll call A1 and B1. Then we have another pair then. I'll go back down to here again. So here we have AI squared is equal to BI squared is equal to 0. And we have BI times AI. Well, okay, is equal to delta I. So if J is equal to I, then we just get the duality condition 1 here. But if I is equal to 1 and J is equal to 2, and we have B1, A2 is equal to A2 times B1 is equal to 0, which just simply means that these are anti-commutative nilpotents then. Okay, B1 times A2 is equal to minus A2 was equal to minus A2 times B1 then. Okay, so now, so again, we define the corresponding mutually annihilating idempotents as UI is equal to BI times AI. Well, if you write that in terms of the bases EI and FI, it's 1/2 1 plus EI times FI. And UI transpose, well, reverse. So we're just changing the reverse of the product, the geometric product here. So we get 1/2 1 minus E1 times, well, EI times FI then.
But here, those are hat elements. all of
Yeah,
this.
they would correspond to hat elements, but again, I'm really interpreting this in the new algebra, which is the tensor product of G11 with itself, really. So it's G11 tensor G11, really. Okay, but notice how I'm creating this new generalized two spectral basis. I'm writing as A1 times A2 times U1 times U2. Okay, so this defines, yeah, UI is just BI. So U1 is B1 times A1, and U2, well, then you change the order of it. You get AI times BI. That would be 1/2 1 minus EI times FI. So again, this is like the other spectral basis that I showed you on the first slide, except now, well, it involves a product of these nilpotents, U1 transpose times U2. And notice that A1 times B2, if you multiply A1, these are nilpotents. A1 and B2 are commuting, anti-commuting nilpotents. So if you square A1 times B2, that thing squared is still equal to 0 because B2 and A1 anti-commute. So you A1 times B2 times A1 times B2, you anti-commute B2 and A1, you get A1 squared, you get 0 here. So these elements have exactly the same multiplication table as the spectral basis I gave you earlier, but they have completely different geometric interpretations. Well, for example, the identity matrix, which is still the identity matrix. See, that's unlike the standard isogeometric algebra. We had e to the phi E1, okay? But in this case, we still have the identity matrix, but now it's interpreted as 1 plus, well, this quantity here is A1 times B1, B2 times, so that's a 4 vector. So in this case, the iso unit, it's not the standard 1, but it's a mixture of a scalar and a 4 vector. Okay, so that's like the iso unit in the geometric algebra then. Well, the iso unit that we talked about in Dr. Santilli's geometric algebra was represented by an iso unit, which is not a diagonal matrix, but this is just the identity matrix, but it's interpreted in this isogeometric algebra as this strange combination of a 1 plus a 4 vector. But again, if you square this thing, you'll find it's equal to 1 again. Or you'll find it's equal to itself. It's an idempotent.
The 4 vector is an element of G22.
That's right. Yeah. So G22, exactly, G22, which considered you can consider that to be a tensor product of G11 with itself. You have to be a little careful. So, okay, so here you have the elements then. You can see the matrix of these elements, E1, E2, E3, and G3 are exactly the same, but they have a different geometric interpretation. So unlike the standard isogeometric algebra that Dr. Santilli defines, I'm keeping the matrix representation to be the standard Pauli matrices, but they represent new elements in the geometric algebra G22, as Dr. Page just pointed out. So A1, yeah. So that's rather strange.
But when you speak about the representation here, you are thinking the representation where? In the iso space or in the standard one space?
Well, that's the interesting thing. As we in the isogeometric algebra of Dr. Santilli, we're reinterpreting the elements of G3. But in this isogeometric algebra, to represent G11, we're really going to a higher geometric algebra. So the actual the matrix 2x2 complex matrices corresponds to an element in the geometric algebra G22, rather than reinterpreting in the standard isogeometric algebra of Dr. Santilli, you're reinterpreting you're giving a different complex matrix representation of the isogeometric poly matrices, the iso poly matrices. Whereas in this case, you're representing the standard poly matrices in a higher dimensional geometric algebra G22. Now, whether these are exactly equivalent, I'm not completely sure. Well, for example, how does it translate to representation theory? Well, the iso Lie algebra is exactly the same as the iso Santilli Lie algebra, because they're generated by the same standard.
I would like to have a few comments, not now, finish your presentation, but this is a very important point. We should discuss it and clarify. You are correct that there are differences, yes, indeed. And I would like to indicate the reason why. But finish your presentation, please. I have no criticism on your presentation. No, I think this is you have made a clear assumption. Those are clear consequences. I see no mathematical inconsistency, none. No, but there are alternatives I would like to bring to your attention.
Well, no, the question that arises in my mind is, can we correspond in a one-to-one way the standard Santilli geometric algebras, isogeometric algebra, with this new idea of representing the standard poly matrices as elements of a higher dimensional geometric algebra? I don't really know the answer to that.
No, there is no, unfortunately, there is no complete correspondence. If you want, I'll make my comments now. For this, I need you to please go back to the equation 15, and if you can. So, and I have to ask your patience because I have to read the equation with my magnifying glass. But see here just a moment. This equation, yes, equation 13. This again, Dr. Sobczyk, is not a criticism. I will tell you otherwise. No, because no, this is you have made a set of formulation and that you derive the consequences. Incidentally, this assumption that you have here, the 13, is also the basic assumption of the paper by the two colleagues from Brazil, the La Rocha and Bass. So the paper by La Rocha and Bass, even though it deals with other argument, other topics, it applies to quarks, but mathematically is fully equivalent and compatible with what you have done. But what I'm trying to indicate is to indicate the differences with what appears in physical papers, and suggest you to, is a constructive suggestion to see whether this difference may give you an alternate, second way of formulating the iso-Clifford algebra. This was my hope. So let's see what the point is. The point is this: this we're talking about the applied mathematics, applied to specific problems. Now, we use this rule 13 in applied in our papers, if and only if the elements A are either number or generally they are scalar. In other words, any quantity whose value has to be an element of the isofield, of the basic isofield. Positively, we do not use this basic rule, namely that A hat is equal to the old A multiplied by the iso unit. Positively, we do not use this rule whenever we're talking about matrices and or operators. And let me elaborate why, and that's the origin of the difference. Now let's go down in this important page where you show that, you see at the very bottom, you show that essentially, I don't know, 17, equation 17. Can you put it back, please? You see, equation 17 essentially show that the isotopic, the isotopic product, let's see this missing on the first step. Let's assume, you know, I assume this is the second. So you have an isotopic quantity A isotopically multiplied by an isotopic quantity Q is equal to the conventional product AB multiplied by the isounit. This positively, we cannot use this assumption, this formulation in physical application. Why so? Because when you compute the isocommutator rule, then the isocommutator rule is identically equal to the conventional for commutation rule multiplied by the isounit. Now, this is mathematically impeccable. Nobody can criticize this. However, I will not have been able to, assuming this rule, I will not have been able to derive the Pauli matrix the way it is derived in foundation of elements of atomic mechanics, the volume 2. Why so? Because Pauli matrices have to be the Pauli matrices are the fundamental representation of the SU2 Lie algebra. Now, to have a complete full 100% isotopy, the iso-Pauli matrices must have to be the fundamental representation of the isotopic Lie algebra, and which means has to be constructed via the representation theory of the SU2 isotopic, and this is if and only possible. I spend years on this point. If and only possible is if the generator of the isotopic algebra, the generators of the isotopic algebra are conventional, the original generator, and so that therefore, when you compute this product is not the product of the two isotopic product of the two generators no longer equal to the whole product multiplied by the isounit, but it's non-trivial. Now, this is by doing so, then this is also physically necessary. Why? Because when talking about, for instance, Lorentz symmetry or rotational symmetry, the generators are the conserved quantities of in physics. The quantities that are totally conserved. For instance, you study a nucleus. A nucleus, you have 10 total generators that are totally conserved quantities. If you want to interpret and represent that nucleus via the isotopy, why? To allow a nonlinear internal interaction, then we must necessarily preserve the total generator because those are physically verified. And this is, if not, this means that, but the generators, the total quad, those are the generators. So again, so in summary, we use this rule 13 if and only if the quantity is an isoscalar, an element of the field. Otherwise, we use the original generators. Now, incidentally, you obtain, notice that before, you correctly, again, everything you said is correct, Dr. Sobczyk. Precedingly, you show that the iso-Pauli matrices are due to all the Pauli matrices multiplied by the isounit. This statement is, of course, 100% correct. It's very, very true. But it is intriguing in my view. Why? Because it's true only for the two-dimensional representation of the SU2 isotopic, at least until SU2 algebra. If you go already at the third, at the three-dimensional representation, that rule is no longer applicable. Then you have to go and separate, apply this rule. You have to restrict this rule 13 only to scalar. But in conclusion, my suggestion is constructive, and I would like to stimulate you to see whether you can reformulate. This will be for the first time. This is suggestion. Nobody, to my knowledge, has done this. Go way beyond the excellent paper by Professor Laroche and Bass, which is also mathematically impeccable. But my proposal is to go beyond, beyond and construct what will be, what in my view will be the true isotopies of Clifford algebra that we can use in physical application, namely which again do not end up with this with the operator, the product operator equal to the whole product multiplied by the ISO unit. Then we remove, then that is, in other words, the Lie isotopic commutator has to be through, you know, operator one, isotopically multiplied by the generator two minus, but this is not reducible to the whole problem. So, in other words, construct the isotopy of the Clifford algebra by assuming as the generator of the algebra the old polymatrices, and use the product to create a novelty. This is basically my so just a suggestion. Maybe it doesn't make sense, but if it is true. But nevertheless, I believe that you have correctly detected the differences between your formulation and what we have done in physics. It's true, they are there because of this reason. Because basically all your results are reducible to a factorization of the ISO unit. No, if I had done so, none of my recent paper, I could not have written none of the preceding paper if I had done so. Because there is no structure from a physical viewpoint. It's just a factor. You are the factor. It's important. There is something interesting to be done. But it's not, in my view, the ultimate. If you want, I can.
That's a very interesting point. I think the difference really lies when you start looking at the universal enveloping Lie algebras. The distinction probably is made at that level between your standard geometric algebras and this new way of looking at it. It should be reflected in the enveloping Lie algebras. Might be quite a different theory. I'm not sure yet about that. I have to.
If you look at if you look at the isotopic theory, you can the totality can be derived from universal enveloping isosociative algebra. But if you look at the definition of that algebra, that algebra, the generator of that algebra are identical to the generator of the original Lie algebra. The only novelty is the isotopic product. And that's why we obtain fundamentally new commutation rules, and with the new structure constant, at times it can be structure function. So we an explosion of novelty from a physical viewpoint. That will be, if you use this rule 13, you lose them all, or most of it. You remain with the degree of freedom, which is the isotopic unit, and there is notice that there is no obligation. In other words, this rule 13, absolute, when you define the universal enveloping isosociative algebra, there is absolutely no mathematical requirement or necessity that I know that the generator of that algebra have to have the product of an ordinary number multiplied by the ISO unit. No, there is no.
I believe you did say that you were very interested in the enveloping Lie algebra of the ISO geometric algebras.
Yes,
but that's a significant point.
But my point is, again, if you are able to develop this from a construct what we call the true iso-Clifford isotope of Clifford algebra, you have something very, very interesting and very powerful. It's worth exploring.
Okay, well, that's interesting.
It's new.
Lots more things to think about.
Again, way beyond the nice treatment by La Roche and Bass. Very, maybe that's why I mentioned that paper, because it supports your presentation, and but I believe there could be an alternative isotopy. Again, starting from the universal enveloping is associative algebra of the iso-Clifford algebra, whose generator are the conventional polymatrices, conventional, and we build everything with isotopic product. that if that is possible, that is extendable to any dimension of the representation, and also it is applicable. For instance, let me put it this way. Remember my paper on the isotopy of the Lorentz symmetry. I could not build that isotopy, those boosts, Lorentz, the boy I call now Lorentz until the isoboost, that live invariant, locally varying speed of light. I could not derive that crucial result if the generator of the Lorentz isotopic symmetry are the whole generator multiplied by the Arso unit. I cannot derive them because the commutator rules are conventional. The structural constants are conventional. Instead, I need structural functions, and the structural functions are the normal, becomes the commutator rules of. I can show to you this now.
Very interesting. So are there any more questions, or should I stop sharing my screen?
Yeah, this will be a fundamentally new way of formulating critical algebra with great, very vast application in physics, chemistry. Chemistry you can apply.
Okay.
Anyhow,
Dr. Sobczyk, did you have a plan to summarize your presentation?
Well, I think that again, I've only looked at the geometric algebras G11 and G3, but the ideas are much more general, can apply to any geometric algebras. Of course, but that's the interesting thing with geometric algebras. It's just a reinterpretation. That's why I consider a matrix is really just a coordinate matrix of many possible geometric numbers. Now, which geometric number is important for whatever physical application, that's where many possibilities arise. But a matrix in itself does not contain metric information. But if you interpret the elements you can give them geometric interpretations, as we've seen now with G11 and G3. But there are many relationships between geometric algebras, and any matrix, whether it's a square matrix or a more general M cross N matrix, you can always interpret their elements. You can always interpret the matrix as being the coordinate matrix of many possible geometric numbers. I suppose that would be a way of concluding my talk. And as far as the isogeometry, and that includes this new way of looking at isogeometric algebras as well. And I guess it would include Dr. Santilli's geometric algebras too. There's nothing, but it'd be interesting to tie the two ideas closer together than I've managed to do so far.
Dr. Sobczyk, I have one additional suggestion for you as a colleague of this seminar. Don't let too much time pass by. Remember, I sent you by email, I sent you yesterday, I sent you a confirmation of the old invitation. My recommendation, put this thing in a paper and have it published again.
Thank you very much. I will certainly do that. I've been, of course, working on.
Future development, you publish it in another paper. But do not wait for additional, for instance, my suggestion of this new class of isoclipper algebra, don't wait for them to publish those results, because the results are important and original and they should be published. That's my suggestion, and we can publish them very quickly on the algebra group and geometries.
All right, thank you very much. I'm just now finishing up the paper for the Ojevich memorial book.
Okay. Very well.
Because I have just one quick and related question is that would you say that that all isogeometric algebras have a matrix representation? Like,
well, that's the interesting thing, is to actually relate. It's just a different way of interpreting the elements of a matrix, really. if you go through a matrix and put 1 in every spot, then you can see you get a geometric number corresponding to that, just delta ij in a matrix can be any 1 and all the rest zeros. And what do those elements correspond to in the geometric algebra? And well, what algebra you're interested in.
Well, but I guess the question that I have is, are there isotopies of Clifford algebra that would fail to have a matrix representation? So maybe my view
Well,
is
that's
a little bit the
of course,
opposite of yours, right? You were saying, well, if I have a certain matrix, what geometric algebras can I represent? But my question is the other way around, that is a possibility of a isogeometric algebra for which no matrix representation is possible?
I think I have the answer in the example. No, the answer is necessarily so, in my view. You have, however, other representation. This is not something that diminishes the value of the iso Clifford algebra. No, you have actually increased their value. The reason is Dr. Page, the answer to this question depends on the actual realization of the iso unit that you select. Everything that we have done so far, we have what are called, the single value theory of mathematics, in which every operation gives the result, one single result. Then within this restriction, I believe that the answer is yes. But the point is, however, that the iso unit not necessarily has to be single value. The iso unit can be multiple value, can be a set, not only in which case you may still maintain ordinary operation or classical operation of view quality, and you can still identify idempotency and this type of things. But then even those ordinary operation or equal can be generalized, and so it becomes hopes and hyperstructure. And but if you restrict the iso unit to be single valued, yes, the answer is yes, because again, you have to look at the head of the whole thing, the universal enveloping iso-associative algebras. Then the product of that algebra, that algebra is interpreted as an envelope of the iso Clifford, and you have an algebra that necessarily must admit matrix representation. Why so? Because the corresponding Lie algebra, because the corresponding matrix representation of the Lie algebra always exists under the assumed condition of regularity, uniqueness, blah blah blah. Then the answer is yes, and this will make them very interesting, because because an alternative to the matrix representation of Lie algebra, the matrix representation of Lie algebra are very restricted. That's why we did the isotopy. So if we have an alternative in terms of matrix representation, in terms of iso Clifford, my God, this is big. This is significant for physics. It's a new approach. It's like changing the glasses and changing the hat.
I guess my question maybe was motivated by just a section of the Rocha and Vaz paper that referred to non-associative isotopy. It's the section 4 of their paper. And so I was wondering if there is a notion of isotopy associated with geometric algebra whose representation would be non-associative and therefore not representable by matrix algebra.
Yeah, no, I have to be very critical on this point. Allow me, Doctor, not over you, my Dr. Page, but and also not against the authors, a lot of La Roche. They wrote a very nice paper. That's why I didn't even contact them. but I have to be strongly negative. The reason the moment you introduce non-associativity anywhere in the structure, you lose. I mean, mathematically it's feasible. That's why the Laroche paper is mathematically impeccable. I have no. However, physically, the moment you introduce a non-associativity anywhere in the theory, you lose the capability of formulating the theory on isofields, and you have all sorts of other. You lose the notion of envelope. And this is the paper that I published. My last paper of physical review, that proved that the theory constructed with a non-associative universal enveloping algebra are physically inconsistent. Mathematically could be intriguing, but physically I will not. I do not know how to. There are too many problems.
Yeah, I just might mention that various authors like Perti Lunesto introduces octonions, and that's of course non-associative in terms of an associative Clifford algebra, but that's different, of course.
But they violated the axiom of a field, so I cannot do physics with octonions. I worked on this point. I worked for years trying to use octonions. The worldwide expert was Professor Lombos from Estonia. And he was a very good friend of mine. We corresponded for years. He was under the USSR domination. When the USSR collapsed, my wife and I, Carla and I, we were in 1992, we went to Moscow, and then by train, we went to Estonia to say hello to the Professor Lombos and discuss things that we had discussed for years. And he was a great expert in so much. He was a mathematician. His work on octonion is unbelievably beautiful. But the conclusion was that the application to physics at this moment, at least at this moment, in any case, a field with a non-associative product cannot be introduced unless there is an universal enveloping algebra based on a non-associative product. So the two things are connected,
but maybe it could be interesting to review the ideas of Professor Rosiewicz about relativity, where he speaks about groupoid formalization for this, and then the problem with the velocities are not they are not associative.
Oh yeah.
They are not associative. And then I think it could be interesting to review this and maybe to check with the ideas that Professor Santilli have expressed before, because it could be interesting to see that demonstrations that not associative algebras are not physical interpretations. Then I think it could be too much interesting, because one of the most important works of Professor Rosiewicz was based in a different set of ideas.
Dr. Cruz, thank you for the clarification. My comments regarding non-associativity are solely and exclusively restricted to the universal enveloping algebra or to field, only there. But regarding the appearance of non-associativity in nature, yes, absolutely. This also was the point, not only that I discussed this with Professor Rosiewicz, but also the point of Professor Lombos, because he had identified a number of situation in nature in which the nature showed the non-associativity, the chaos theory, and also statistical mechanics, and so by no means I am saying that non-associativity should be excluded from physics. No. Thank you for the clarification. No, only that actually I can tell you, I personally believe that that we will reach a better understanding of gas when we admit the non-associativity of the event and its interior. The scattering in between molecules is not necessarily associative. No, and the best way to represent it is as a non-associative collision. In the sense, it's not transitional. It will not propagate identically from one to the other. No, there is a discontinuity. This discontinuity or propagation of the event can be best represented by non-associativity, in my view. Yes. So thanks for the clarification. For algebra, you saw only for isotropy of the algebra, and also non-associative algebra very interesting. So no, only for isotropy.
Just to follow up a bit, Jesus, on your comment about Shevich, of course, his main concern about non-associativity and composition of velocities was he usually viewed it as a criticism of relativity itself, conventional relativity, that this composition could be non-associative. So much of his work was to try to resolve this by defining compositions that were associative, or by redefining what was meant by velocity, so referring to binary velocity.
Certainly,
So
when you give up associativity, you make calculations much more complicated without associativity.
Oh yeah. But for the case of the special relativity implies a structural generalization. From the moment you introduce a non-associativity anywhere, you really have a broader theory and perhaps more adequate to represent the complexity of nature. We just discussed the complexity of the event inside the gas,
Well, for me, the most obvious connection with associativity is whether or not interactions can be viewed as pairwise or not.
Can you repeat, please? Can you repeat, please?
So my claim would be that if the relationships are associative, then all interactions can be viewed as consisting of pairwise interactions, so we can have a system of, say, n bodies. We need to only consider the interaction between pairs of those bodies, like so. But the possibility does exist that perhaps there are interactions in which more than two bodies are involved. This occurs, for example, in quantum mechanics. That there are situations in quantum mechanics where the apparent interaction involves three bodies irreducibly, so that we cannot reduce their interactions to just interactions between pairs of those bodies. There's a very famous geometric example of this, and I forget exactly the correct name, but it consists of three rings that together as a combination of three rings, you can form a geometric topological ring that cannot be decomposed. But if you remove any one of those rings, then the two rings are separated. But when you have three rings sort of wrapped in a sense, they can move over top of each other, but can never be separated. So one takes this geometric picture as a demonstration that these three things interact in a way that cannot be described just in terms of the pairs of those rings alone.
Of course, then you asked a question about four. Maybe there are interactions requiring four or more bodies. Why we stop at three then?
Well, yes, of course. So if we require four bodies, or if we require n bodies, then the complexity of the interactions rises exponentially, right? Rises. But if we can reduce all interactions to pairs, then this is at most sort of polynomial complexity, or quadratic complexity, right?
Let me give you an example. An example along the Professor Sevich thinking of an n body. Consider a portion of water, some ordinary water. All the atoms of the water, they are entanglement. They are bound together. So now, suppose we transform the original drop of water into vapor. Then the particles are entanglement. They are entangled because they were originally the part of the same body. So their wave packets are coherent, are entangled. In conclusion, if we want to look at the interaction among of this gaseous form of water, and all of them participate, because with EPR entanglement, you automatically bring the individual. You have to complement each individual reaction of an elastic on elastic between the molecule, but you have to complete it with the contribution from all the entanglement of each member of the pair with all the rest of. So the answer is yes. The non-associativity is inevitable. Yeah. It's very intriguing. In the future, it will be inevitable to study this contribution. I mean, now we cannot measure the contribution of the EPR entangle in the case of the evaporation of water is so small that our technology cannot even measure at this moment. But we believe that it exists, and sooner it has been measured classically. The entanglement of particles has been measured among classical macroscopic oscillator. This is a paper on from Physics Today of a year ago. So the entanglement is a physical interaction that actually exists and is n-dimensional. It's n-dimensional in the case of gases. This is a very tricky problem.
So perhaps we should say that our meeting today can come to a close. Before we do that, though, I should ask whether there are proposals for presentations in the future. Would you do you think that following this talk or any of the preceding talks would justify scheduling a meeting devoted to discussion on general topics, or should we consider delaying for the next meeting until someone expresses a desire to speak on a specific subject? I'm just open to proposals for what we should do in the future.
Personally, for a few weeks, I'm very, very taken with an important commitment, but certainly I'm available for discussion. And then Dr. Page, you know my field of research. If you want me to present a topic, you pick it up among the past correspondence. Give me a week or so to prepare it, and I will be delighted, but with no obligation, and it's up to you, entirely up to you.
Okay. Dr. Sobczyk, you mentioned that you would be continuing your research also on the idea of representations or enveloping algebras and so forth. Do you anticipate presenting something on that subject in the next?
I don't think I'll be ready in the next week or two, but I'd like to get back to your ideas of this idea of Ojevich with the three maybe limit our 3 interactions. I'd like to understand that better. If you'd like to present something more on that, or maybe we could somehow
Dr.
proceed in that direction.
Dr. Cruz, could you please review it for all of us, including myself? I must confess that I have a nebulous recollection. Is a point so important?
Excuse me, I don't understand the point.
No, could you please review this aspect regarding the three vectors, the non-associativity for 3 vectors? Because in my memory, the discussion with
that's true. Yeah,
I don't remember it all correctly or in details, and it is a very important point for new insights.
Yes, maybe I like it to speak about this, but in the context of the work that I was making around interaction. I think that this can be a good point, but I do not can be ready for the next week for this presentation. Maybe in 2 weeks this can be made better.
Be great.
Yeah, that sounds very interesting, especially the connection with the interaction theory as you presented it so far. I would be very fascinated to understand how this interaction theory could be possibly extended to being involving more than 2 bodies.
Okay.
I think that would be very interesting, and if at the same time you could relate it to the idea of non-associativity, where it occurs in the conventional definition of composition of velocities in relativity, I think that would be a very interesting result. So I think I like that proposal, perhaps that we could delay our meeting for 2 weeks. And then if you feel that that's sufficient time, Jesus, then I think it would be very good to continue with the presentation and discussion on that subject at that time.
Okay. Thanks a lot. Yes.
No, thank you.
It would be interesting to consider those points that you're talking about in relationship to Olszewicz's ideas too, of course.
Okay.
Well, thank you very much, everyone, for attending. And I would mention just that we did have one extra member. He didn't speak up, but Darius Shrebek was also listening in. And so I hope our presentation today was useful for you, Darius.
Yes, this is Dariusz Świerk. I'm a former Professor Olszewicz student. Currently, I'm reading a lot about isoalgebras, and this is something quite new for me. And I'm trying to I'm writing a small paper, something like an introduction for beginners, complete beginners, because I was beginner a month ago, tried 4 times to understand what the ISO mathematic is, and after correspondence with Professor Santilli, thank you for that, Professor. Finally, it dawned to me that it's something really big and not quite complex. So I might be someone who starts in this field and who will gladly attend any of your presentation, because I see these ideas in practice. I have a background in differential geometry and Professor Olszewicz ideas, and I find this topic and your presentation extremely interesting. However, I must admit that I am not prepared to give some presentation, and my level is still at the beginning. I plan to write something about ISO numbers, ISO vectorial, ISO differential geometry. Let's say, this would be my favorite topics. So, thank you.
I think that's excellent, and I encourage you to ask questions and
Okay.
in writing or during the seminar.
Thank you.
I think it's very valuable to have someone who is learning the subject from the beginning to ask questions.
Very valuable here for us to understand better what we have been doing.
Yes, exactly.
Why don't we have an open session with his question and discussion and open discussion? It would be very helpful to everybody, because concept that not to mention all the issue, but just the complexity of the notion of ISO unit.
Yes.
A number of different realizations.
Yes.
Very legitimate question. So please, why don't you organize a session with our guest as the main speaker in the sense of, and we discuss it, and be fantastic for everybody to see the alternative.
And of course, as a speaker, you can simply ask questions. I think
yes.
this would be this would be very useful.
Okay.
Okay. Well, thank you very much, everyone, for attending.
Thank you.
That's
And
implies a knowledge, because just to ask the question implies a certain knowledge.
Yes, it's a fascinating topic, I must admit. So thank you for this possibility again.
Of course, anytime.
Okay. So we will meet again in 2 weeks. We'll be discussing non-associative interactions, I guess, or perhaps the uses you can submit a more relevant topic title if you prefer. But then at some time in the future, after that, we will have some open discussion of the kind that's suggested by Dr. Santilli.
Thank you.
Okay, thank you very much.
Thank you very much. Thank you.
Bye, everyone.
Goodbye, everybody.
Thank you. Bye-bye.
Thank you.